All right. So thanks everyone for coming out. For those of you who don't know me, I am Jerry. I'm Director of Tech for RAS, and today we're going to be giving you an overview of what motors are, how they work, how we can use them. All right, so first things first, what are the things that we're going to be addressing in this presentation? We're going to be looking at what kind of motors are out there and then how you kind of figure out which ones are best for your application. And then we're going to be taking a look at how exactly each of these motors work, as well as once you know what kind of motor you want, how do you figure out what size you need? And then we're going to be looking at a few examples of how you can actually use those motors and what else you need in order to run them. So to start with a more general definition, motors in a general sense take one form of energy, whether it is chemical or electrical, what have you, and convert that into mechanical energy. So in the case of in the visual you see here, we have these pistons expanding and contracting, likely due to the combustion of a gas. So in that case, that would be chemical energy. And then that expansion is being used to rotate this output shaft, which then converts the chemical energy into mechanical energy. Now, in this presentation, we're going to be focused entirely on electric motors. So taking electric energy, voltage, current, what have you, and converting that into the rotation of an output shaft, mechanical energy. So there's three specific motors that we're going to be looking at in this case, DC motors or direct current motors, stepper motors, and then servo motors. So DC motors are sort of like the entryway into electric motors. They're by far the simplest and the cheapest that you can get for these sorts of systems. And really they are designed for applications which have very high speeds that require continuous rotations. So an example of this would be like the motors on like a car. Now, how exactly do DC motors work? Well, so DC motors are very simple to wire. They only require power and ground. So when you supply that voltage, a current is going to enter into the motor and be applied by these brushes and contribute current through these electromagnetic coils. Now, for those of you who have taken Physics 2, this may look scarily familiar to you, but for those who haven't, when you send a current through these coils, the surrounding magnets on the outside you see here are going to produce a torque on them. So then this torque is going to cause these coils to rotate like you see on the right-hand side here, and that's how we generate the rotation of the shaft from the input electrical energy. Now, what you see here is an example of a brushed DC motor. When you're looking at DC motors, you're going to see a question of brushed versus brushless. So brushed is what we just saw, where you have these coils on the inside that have a torque applied to them by the external magnets. In a brushless DC motor, you actually have it flipped. So what you have is you have coils on the outer edge of the motor, and you essentially apply current to each of them in turn through a series of pulses. And by rotating and by changing which one you're applying current to, you generate a torque and therefore a rotation on this central magnet. And this central magnet is what's going to rotate the output shaft. So when deciding which of these you want to use for your DC motor, in general, brushed DC motors are going to be cheaper and easier to program. Like I said, they're the entryway into motors, so they're the easiest to work with. But at the same time, they also generate a lot more heat and a lot more friction because of the brushes making contact. So in general, you're going to have a lower efficiency and a much shorter lifetime because there's a lot of wear down on those brushes. Now, a brushless DC motor is going to generate a lot less heat and have a much longer lifetime because there's no longer any contact. So there's not going to really be as much friction. So because of that, you can also reach much higher speeds, actually. The main downsides for these are that they're actually more expensive and they're more difficult to program because you have to deal with what's known as an electric speed controller, which is going to be used to dictate the pulses between each of these coils. So in many instances, you'll find that when looking at other robotics projects, brushless motors are starting to replace brushed motors. But as long as you aren't concerned about the lifetimes and you have a brushed DC motor that will satisfy the speed requirements you need, a brushed DC motor will usually work just fine. Now, the next example is going to be a stepper motor. So stepper motors are designed primarily for lower speed applications, and they have a very high holding torque. What a holding torque means is that basically if I'm trying to force the shaft of this motor to move, I have to apply a lot of torque before the motor essentially gives in and will rotate. So these are a bit more complex than a DC motor, but the main benefit of these is that they have a very precise position control. So generally the rotation of a stepper motor is defined by its resolution. So in terms of steps per revolution. So most commonly you'll see stepper motors that with a resolution of 200 steps per revolution. So a stepper motor, when it moves in individual discrete steps. So if a single revolution is 360 degrees and you have 200 steps per revolution, every individual step is going to be 1.8 degrees. And that's going to be very precise. There's going to be very little error within that step size. And then you can also, through a couple different ways of programming these motors, you can make that even more refined. For instance, you could do half stepping and reduce that from 1.8 degrees to 0.9 degrees per step. So while the speed is generally lower for stepper motors, there's a lot of applications where precise position control is required. For example, looking at 3D printers, for instance. So in those applications where you have to know exactly where you're going to be, stepper motors are an ideal choice. So stepper motors work in a very similar way to brushless DC motors, where the rotation of this internal magnet is going to be dictated by the current through these coils here. And by carefully changing which coil you're applying current to, you're able to generate those discrete exact steps. So the last motor that we're going to be looking at here is a servo motor. So servos are actually just DC motors, but with extra steps. Servo motors already include the DC motor, but they have an additional gearbox, a control circuit, and a position sensor, which is often a potentiometer, I believe. So in this sense, they're very similar to a DC motor, but all the external components that you could add yourself are already enclosed within a servo motor. So because of these additional components, servo motors are very good for both high speed and high torque. The main downside of the servo motors is that they're often limited rotation motors. So in many cases, you'll find that a servo motor will only go from 0 to 180 degrees. So they're not really designed for continuous rotations like a standalone DC motor is. Which is why in a lot of cases, you'll actually see servo motors in things like robotic limbs, because the limited rotation isn't really an issue for a limb, like for instance, your elbow joint. And the high speed and high torque is very beneficial. So looking at how they work, on the left-hand side, you see that DC motor down there. And then with the gearbox sitting on top up here. This gearbox will connect the output shaft of the motor to the output of the DC motor to the output shaft of the whole system, as you can see over here. And then on the bottom side, you see this control circuit connected to the position sensor. So you're actually able to measure the position and respond accordingly based on what your desired position is for the output shaft. So this is just this slide is really just to show a more direct comparison of these three. A quick recap is that a DC motor is great for high-speed, continuous rotation applications like wheels. Stepper motors are great for precise position control, but have a typically lower speed. So things like 3D printers that don't really have to move that fast, but need to know exactly where they are. Then a servo motor has high speed and high torque, but you're often limited by the rotation. So things like robotic limbs, and in some cases like RCs, also make use of those. So one thing you may have noticed in the discussion of what each motor is beneficial for, it often comes down to what torque you need and what speed you need. So when you're choosing a motor, in addition to the context of the application, you also have to consider how the torque and speed requirements for your specific robot. So all motors are going to have some kind of trade-off between torque and speed. And we're able to represent that with what's called a torque speed curve. When you're going to be selecting motors, it's important to sort of get comfortable with how these look so you understand exactly if a motor will be able to work for your project. So a few key terms here is going to be the stall torque. The stall torque is essentially the maximum torque this motor is able to supply, but by supplying that torque, it's also not able to generate any speed. This is the absolute max it can supply. So it's similar to a holding torque in that sense. Conversely, you also have the no-load speed. The no-load speed, essentially, if you were to just supply power to the motor and let it run, that's the speed that it would run at, because you're not applying any additional torques. So then we are then able to essentially connect the dots between these two and generate what's called the torque speed curve. here we have a linear setup, which works very well for DC motors. DC motors have a very strong linear relationship between torque and speed, but it doesn't necessarily work as well for stepper motors. Stepper motors are what you see here on the right. And we kind of see it based on this plot that the linear relationship does not quite hold nearly as well. So when you're looking at this torque speed curve, in order to figure out if a motor will work for your application, the torque and speed that you need for your system ideally is going to end up down here somewhere beneath this torque speed curve. The curves you'll see are going to be given for a rated voltage, which is the generally the maximum voltage you want to supply to a motor. So, which is what you see on this blue line here. So then we're actually able to adjust that voltage by adjust that curve by modifying the voltage you're supplying to those motors. However, you don't generally want to go above this curve because that's going to cause issues with the lifetime of the motors. But anything beneath this curve is going to be fair game because we can reduce the voltage we're supplying to the motor and therefore give us access to essentially any torque and speed underneath this plot. So we know what we're going to use the torque and speed requirements for, but how do we figure out what those are? So again, that's going to really depend on the context. When you're considering what you want to design, you have to ask yourself, how fast do you want to go? And just as importantly, how quickly do you want to reach that speed? So you need to consider both velocity and acceleration. So then based on the speed, you have to look at the torque and essentially consider how much torque do you need to reach that speed. So let's take a look at a quick example. In this case, we're going to use SumoBot, which is a common project that many of you are on actually, that RAS does every year. So let's say my goal for SumoBot is to reach a speed of 1 meter per second in 1/4 of a second. So what we want to do is we want to figure out what size motors we're going to need for this application. So here are just some general specs. Mini Sumo is typically about 600 grams. It's a wheel diameter of 38 millimeters, which is about 1.5 inches for those of you who hate the metric system. And then it has 4 driving motors, meaning each wheel here is going to have its own motor. So let's start off by considering the speed of the system. In the problem statement, we decided that we wanted to have a maximum speed of 1 meter per second. So that's going to be the linear speed. When we're looking at motors, we have to consider the angular speed, essentially how fast the motor is rotating in order to create the linear motion of the robot. So we can use this relationship, V equals omega R, where V is the linear speed, omega is the angular speed, and R is the radius, in this case, of the wheel. So by solving for that, we get an omega, the angular speed of 52.6 radians per second, but most spec sheets will give that information in terms of RPM, or rotations per minute. So if we convert that from radians per second to RPM, we get about 500. Next, we need to actually consider the torque of the setup. So what we can do is we can start off by considering Newton's second law. Essentially, we want to start with Newton's second law because in order to generate a linear velocity, we need a force. In this case, the force is going to be applied at the bottom of the wheel where it makes contact with the ground. So Newton's second law is just F equals ma. Note that in this case, we are dividing it by 4. Because we have 4 driving motors, each individual motor only has to provide 1/4 of the total force. If we had 2 driving motors, we would just divide this by 2, or if we had 1 motor, it would have to provide the whole force. But because we're dealing with 4, each motor itself only has to provide 1/4 of that force, and therefore 1/4 of the torque. So from the problem statement, we found that the acceleration, we know that we want to get to 1 meter per second in 0.25 seconds. So it's going to be an acceleration of 4 meters per second squared. And that is going to correspond to a force of 0.6 newtons. So then looking at the equation for torque, torque in general is just going to be F being the force times the radius. So then we can find that the torque is going to be 0.0114 Newton meters. However, again, much like with speed, those aren't the units we commonly use for these applications. Smaller motors give their torques in ounce inches typically. So if we make that conversion, that's going to be 1.6 ounce inches. Okay, so we made those calculations. We know what torque and we know what speed we need. Then how do we actually begin looking for a motor? So At this point, it's just time to start browsing and looking at different websites. In this case, I'm going to be using Pololu because they have a lot of great small motors that are available. But at the end of the presentation, I have a list of websites that you can use to get started on looking for motors and all the other components you'll need for this. So we're looking at a continuous rotation application. As we discussed before, that's going to be ideal for a DC motor setup. And then for this context, we're going to be using a power supply of 6 volts, which is relatively standard. So in general, you're going to be start looking at the specs of the motors provided by the vendor. In general, you'll be given the rated voltage, the no load speed, the stall torque, and those are going to be the main ones you're concerned with. So right off the bat, there's a few things that we can take a look at. All these motors down here have a no load speed that is lower than 500. So even if they satisfy our torque requirements, it can never meet our speed requirements. So we can already, right off the bat, just ignore those. And then looking at the stall torque, we know that we need a stall torque of 1.5 ounce inches. And this one can only give a stall torque of we need a stall torque of 1.6, and this one can only provide 1.5. So right off the bat, we can ignore that top. So now we see that we have 4 motors that may work based on their no load speed and their stall torques. So now what you have to do is you have to start taking a look at the actual torque speed curves to consider where underneath that curve your design point is going to land. So in this case, let's take a look at this motor here, which has a no load speed of 1,000 and a stall torque of 7.9 ounce inches. So here we have the torque speed curve for that exact motor. In general, when looking at vendor spec sheets, you're going to find torque speed curves that have a lot more than one curve. In this particular case, we have several other curves. This green curve is showing the efficiency, this yellow curve is showing the power, and this red curve here is showing the current. And then this blue curve, this is the one we want. This is the torque speed curve that we're trying to look at. So let's start off by figuring out where our design point is going to fall exactly on this. Now I've kind of spoiled it here, but for sake of argument, looking at the torque, we know we said 1.6 ounce inches, which for this graph is going to correspond to 1.1 kilogram millimeters. And then a speed of 500 RPM is going to put us right here. So this is actually a very good point to be at. We are well below the curve of the rated voltage, so we have a lot of wiggle room in case we need to go a little bit faster or apply a bit more torque. So there's a good factor of safety here. Now, one thing you'll find is that there's going to most likely be multiple motors that satisfy your requirements. For instance, if we looked at a couple of the other ones that I had listed in the previous slide, we would have found several others that would have also worked for this. So how do you know which one is going to be best to use? So there's 2 things that I would recommend you consider. The first being the current. So looking at this current curve, we see that we have a relatively low current. And as you increase the torque, that current is going to increase. In general, if you can choose between a higher current or a lower current, it's better to choose the motor that will use the lower current. Typically, if you select a motor with a higher current, you're limited in what other components you can use with it, because not many electrical components are going to be suited for a higher current compared to a lower current. You can also consider the efficiency of the setup. If you are working with a motor at a lower efficiency, it's going to dissipate more heat, more wear on the brushes, and it's not going to last nearly as long. So if you're able to, it's better to try to operate at a point closer to where the maximum efficiency of the motor is, which in this specific case, we're actually very close to. So this is actually a very good motor for what we pick. It has a nice factor of safety, a comparatively low current, and then a nice efficiency as well. Now, one thing that is good to keep in mind is that just because a motor satisfies both the torque and the speed requirements, looking at the stall torque and the no load speed, does not mean it can satisfy both at the same time. So let's take a look at this example here. We have a no load speed of 860 and a stall torque of 2.4, which sounds great on paper, sure. But if we consider the actual torque speed curve, we find that our design point is outside of this curve. So this indicates that even if we were to use this motor at its rated voltage, we still couldn't reach the torque and speed that we need for our application. So it's very important that when you're considering what motors to use, you're actually looking at the full curve and not just the specs listed on the vendor's website. Okay, so we picked the motor. That's great. But now what else do we need to do in order to actually make this thing work? So in many cases, you're going to need an additional piece of electronics that's going to be used to regulate the speed and direction of your motor, and that's often referred to as a driver. In the case of DC motors and stepper motors, it's especially common to use what's known as an H-bridge. On the right-hand side here, you see a general schematic of what an H-bridge looks like. And the whole idea is that with the H-bridge, it will automatically flip a direction for you, depending on what signals you provide to the H-bridge. So this kind of helps handle a bit more of the control of it without you having to directly code it into your system as much. Now, when you're picking out components for your drivers, it's important. This is where the current is going to become especially important, like I mentioned before. Motor drivers can only handle a certain amount of current. So when you're selecting one, you have to consider how much current your motor is going to draw when you're powering it. In the case of our motor, we are actually have an operating current of about 0.38 amps. And this particular driver can support up to 1 amp or 600 milliamps if we use a different version. So in this situation, this is actually a very good spot to be in because the current we're going to be using is going to be well below the rated current for the system. Now you may find that it also lists a peak current as well for the motor driver. In general, you don't want to rely on the peak current for the driver. The peak current is not intended for sustained use at that current. It's meant to be short instances of reaching that current, but in a more general sustained use, this can support 1 amp, but 2 amps is limited to very short periods. So in addition to the driver and the electrical side of things, you also want to consider the mechanical components of your system. If you want to mount a wheel to your motor, for instance, you may have to consider buying wheel hubs in order to actually mount it. Or let's say you already have wheels, but the shaft of your motor won't fit into the wheel hub. In that case, you have to buy a shaft adapter to kind of fill in that gap. You also have to consider how exactly you're going to be mounting your motors into your system. In many cases, like stepper motors, you're able to buy standard mounting brackets that you can already use. But for some instances, like what we find at RAS with SumoBot, we actually will often 3D print our own motor brackets and build them directly into the system. So it's important to consider that as well when you're deciding on what motor you're going to be purchasing. So let's start looking at how exactly we can control this system. I mean, knowing what motor to use is great, but how do you actually use it? So there's 2 key things to consider: direction and speed. So direction is often handled by an H-bridge or other driver itself. Generally, you can give the H-bridge either a high, being a 1, or a low, being a 0, and each one will correspond to a different direction. So depending on what signal you give, the H-bridge will tend to handle that automatically. Alternatively, if you aren't using a driver, for instance, you just need to flip the voltage. So if you supply a voltage one way, and that's counterclockwise, if you flip the direction of that voltage, it will turn clockwise. So then the other important component here is going to be speed. In the case of DC motors, we typically use what's known as pulse width modulation to supply a voltage that's going to decide on that rotational speed. So what is pulse width modulation? So when dealing with digital pins, they usually communicate in terms of high and low, like I said before, where high will correspond to your power supply, so like 5 or 6 volts, and low will correspond to 0 volts. If you only use high and low, it's very difficult to get those intermediate speeds, because I mean, high is going to correspond to the full output of the motor, and low is just going to be, it's not moving. So how do you get those intermediaries? This is where pulse width modulation comes in. With pulse width modulation, we're essentially turning that pin off and on very quickly. So it's going from high to low in a very quick state. But because it's happening so quickly, the motor and the driver do not interpret it as that. They don't interpret it as this sort of step function like you see here. It's interpreted as an average voltage. So we represent that using what's known as a duty cycle. So a duty cycle refers to the percent of time that the signal is at the high value compared to the low value. So a 25% duty cycle means you're at high 25% of the time and low 75% of the time. And that would correspond to an average voltage that is 25% of your high value. So if your high value is 5 volts and you have a duty cycle of 50%, the average voltage is 2.5 volts. So by adjusting the duty cycle of your PWM, you can then get all the intermediate speeds between your low and high outputs. Now, before we move on, let's distinguish, there's actually two different kinds of PWM that you can use. There's hardware controlled and there's software controlled. Many microcontrollers already have PWM built into their systems. So there's certain pins, as you can see down here in the case of this Arduino Nano, that can already be used for PWM directly. So this is actually much simpler to control. But the main downside is that if you want to use hardware PWM, you are limited to these pins exactly. If you want to use any other pins, PWM, you have to use a software-based one. Where essentially what you're doing there is you're using the controller's timer function to make your own PWM loops. This tends to be more complex, but you have a bit more flexibility in terms of what pins you're able to use. So let's take a look at one example of a motor code just to give you an idea of how that's actually going to look. So here we just have a brief code that we've used in a previous project just to make sure that the motors were working as we expected to. So in general, the first thing that you want to do is define what each of your pins are. As you can see up here in the case, in this case, we define the right-hand side motor, the pins for the right-hand side motor. Here, where we have a pin 10 for PWM, and we have the input pins to the motor as 4 and 7. So in this particular case, we're actually not using an H bridge. We are just connecting the motors to the controller directly, which is also doable, but you have to make sure that you're programming the direction control directly into the program. And it also requires an extra pin, whereas an H bridge would only require one pin. So then we also do a similar setup here for the left-hand side motors. So then once you have your pins defined, you can move into your setup function. Your setup function is going to be quite simple for motors. Everything is going to be outputs. From the motor directly, we're not taking in any information. All we're doing is telling the motor what to do. So every single one of these pins is going to be an output. And then you can get into the loop function. The loop function being essentially what your robot's going to be running the entire time it's on. So when we're looking at the input pins to the motor, we're going to be using digital write functions. These are just going to be highs and lows, because all we're doing now is telling essentially what direction the voltage is going to be flowing in, or the current is going to be flowing in, rather. So in the case of the right-hand side motor, let's say we want it to rotate counterclockwise. In this case, I will set the first right side pin to high, and then the second right side pin to low. If I wanted to rotate in counterclockwise direction, I would just flip this, where this first pin will be low and the second pin will be high. And then I can do a similar setup for the left-hand side motors as well. So then looking at how we actually define the PWM signal. This is going to be an instance of hardware-based PWM, because we're just using the PWM pins that were directly built into the controller. So PWM signals are going to be dictated by this analog right pin, because you're not really, when you're defining a value for this pin, you're not giving a high or a low, you're defining it based on what duty cycle you want. So in this case, you can define a duty cycle based on values from 0 to 255. Why 0 to 255? Well, this is an 8-bit system. And when you're working with an 8-bit system, this is the range of values you're able to use in terms of binary. So in this situation, a 0 would correspond to a 0% duty cycle, and 255 would correspond to a 100% duty cycle. So essentially, we can use any value in between there to represent what duty cycle we want. In this case, we have a value of 127, which is right smack dab in the middle. So that would be a 50% duty cycle, or half the speed of the motor. So that is a rough idea of how you can set a direction, and then you can set a speed within your coding. Let's say, for instance, I want the motors to stop. If I want this thing to not move, all I have to do is set both of the input pins to high. By setting them both to high or both to low, you are actually able to, there's no voltage difference across the motor, there's no current flowing. So therefore, there's not going to be any rotation. So that is just a quick example of what that code could look like. Obviously, you can get much more complex than that, but that's just the basic idea of how to get those motors moving. So this setup that we have right now, which is just the controller, driver, and then motor, this is what's known as an open loop control system. That means we're just saying what we want, and we expect the motor to go do that. This is compared to a closed loop system, where in a closed loop system, you're actually measuring what the motor is doing and using that feedback to dictate what the controller is saying. So if we have an open loop system, meaning we don't have feedback, we can't be 100% sure what our system's doing. So let's say we tell our robot to move 1 meter at 1 meter per second. Well, how do we know for sure that we moved that far? And how do we know that all the motors are moving at the exact same speed? In general, the internal components of a motor may be different from one to the other. One may be more worn down, or the imperfection of the controller may supply a slightly different voltage to one motor than the other. So in that case, oftentimes the motors are going to be moving at different speeds, even though you give them all the same input. So how can you be sure about what's actually happening within your system? So in the case of motors, we actually often use encoders. With encoders, we're able to measure both the motor's true velocity and our position. Down here, there's actually a wide variety of encoders you can use. These are just two examples. But essentially, how they most often work is you have this disc here or here that attaches to this shaft here. This shaft will rotate along with the motor shaft, and this circuit board here will essentially count the number of rotations. So let's take a look at exactly what that looks like. So generally an encoder is going to have two pins that are doing this measurement. Why do we have two pins? Well, by having two pins, we're able to not only count the number of rotations, but also the direction of which way this thing is rotating. Let's take a look at this graph on the right here. Well, this image on the left here, rather. Here we see that when there's nothing here, A will turn on, and then when something's in front of it, A will turn off. And the same is true for B. So because this system is rotating clockwise right now, we see that A actually turns on first, and then A will also turn off first. So when you're recording the two step functions you get from this, we see that A is actually leading B. So A turns on first, then turns off first. So because we know that A is starting first, the system's going clockwise. By that same token, if we're moving counterclockwise, B will turn on and turn off first. So by figuring out which pin is turning on and off first, we know exactly what direction we're moving in. So with this setup, we are then able to count the number of rotations in each direction, because every time this thing turns on, a certain number of counts will correspond to one total turn. So then we can relate that information to velocity and position data. Knowing the diameters of the wheels, we are then able to take the total rotation that we've counted and convert that into a position of our system. Similarly, we could also, if we're measuring the time as well within the internal clock of the controller, we can then convert that rotation into angular speeds. So then we can directly compare the speeds of the different motors to see which one's matching up. So for instance, if one of the motors is moving a little bit slower than the other, I can increase the duty cycle to assign more voltage to help compensate for that. And then similarly, let's say I wanted this thing to move 1 meter like before. So then I'm measuring the position and I find, okay, we've hit 0.9 meters. Maybe I should slow down and get ready to brake. Or maybe I've overshot. Maybe I read 1.1 meters. Well, in that situation, I know that, okay, I went too far. I have to back up and get to the right spot. So by using these encoders, we're able to get a much better understanding of what our robot is doing and how we can correct when things are going wrong. So this presentation has given you a lot of the tools you'll need to get started on constructing your own systems and using motors for your own projects. Let's recap a few things that we've gone over. So there's several electric motors you can use for various purposes, whether that's DC motors, stepper motors, or servo motors. To figure out what size motor you need, you're going to have to do some type of torque analysis to figure out your speed and the required torques. And then in the case of DC motors, you're able to control that speed and direction using a PWM signal. And then lastly, you're able to generate a feedback loop and measure what your motor is doing using an encoder or some other similar sensor. So these slides will be made available to everyone, I think, they'll either go in the Slack or up on our website. But these are just some website you can use to get started on what you're looking for. Pololu and SparkFun are great introductory websites. They have a wide variety of products. If you're looking for more specific stuff for motors, places like ODrive, Servo City, and Stepper Online are going to be a great resource for you to use.